Okay. Yeah, yes, everybody. Okay, ladies and gentlemen, what I want to do now is just to quickly talk about convolutional neural network, which essentially deals with image. There's the general term that is used for image processing. We call it computer computer vision. Okay? And this, under this you have character recognition, you have general image processing, you have signal processing, not the type of signal processing you have in network communication. It's a different type of signal. It's a signal that actually is more or less like a camera. Okay? It sends something, it takes the picture. It's like, sensor processing, sorry. It's like in the security, home security alarm system, where you have camera at the door. So that camera comes with a sensor. It discovers the presence of something through its radiation, and then the camera will flash, and then the image will be stored. So all those things can be processed using the so-called convolutional neural network. Actually, the term convolution comes from computer vision, from image processing. It's not part of machine learning. So the term convolution itself comes from there. Okay, that's one thing I want to say. Where's Tolu? You are there. I know you are doing something on TensorFlow. There's the idea of filter, stride, and padding. You should have come across that on your TensorFlow. I will explain that later. One other thing, image, generally, when you have image of anything, probably I use something here, just quickly. So here I have image, this is an image of the digit 7. As it is, it's not useful for any machine processing. Okay? This could be a picture of somebody. It could be MRI output. It could be CT scan. It could be echography, that is ultrasound or image. It could be anything. But as it is, it's not useful. Okay? So what happens is that image like this is converted into pixel. Okay? So this is the pixel for 7. Because this is black and white, you can easily see it is a two-dimensional thing. Okay? And you can easily recognize the 7. Look at it there. You can easily recognize the 7 here. Okay? So the places where you have 0 are the places where it's white. So it's white and black, white. So the places where you have 254 up to 256, that's the place is dark, black. In between is gray. Okay? So this is what you send into your machine learning. Not the 7 we saw before. This is the 7 you send into your machine learning. And then we refer to each one of these as pixel. Are you with me? So if you now want to deal with cancer whatever prediction, and then the images are produced making use of an MRI machine or X-ray machine or CT scan machine, whatever it is. All those images need to be converted into that form. Are you following my argument? No. So when you go to a website to download data on images, this is what you are downloading. Okay? So we agree with that. Now, in the case of black and white, it's only black and white. It's a two-dimensional thing. In the case of color, it's a three-dimensional. Okay? So we settle that. So let me go to my convolution now. I think. Great. So we are back here. And click. So now, when you have your data now, which are in pieces, okay, they need to be filtered in order to recognize not just the edges, but the image itself. Filters allow you to do that. Okay? Number two, filtering also allows you to be able to reduce the size. For example, we have a 28 by 28 matrix. We can use filter actually to reduce it to 7 by 7 so that the size is reduced for computational purposes. Okay? So the question is, what is filter? Filter simply, that's what we call convolution, is a matrix, it's a vector. If it is black and white, it's a two-dimensional matrix. If it is color, which means red, blue, and green, those are the primary color that you can use to determine any other color. So it's three-dimensional matrix. The filter is three-dimensional matrix. So, and this is referred to as convolutional kernel. Now, there are some specialized type of filter that are used in image processing. We'll see an example later on. But filter in general, this is this representation. Now, I know this is mathematics, some people, but I will explain. It's simple, okay? What are we saying? I pick black and white image. My X represents black, my Y represents white. That's what it means, okay? And then, my filtering is actually a computation, which is that dot product. It's a computation, that dot product. So, I'm now applying the right-hand side. I'm applying, in order to obtain my I, I need to do this. In order to obtain my K, it has to fill in with those two. And the result that is returned to me, to the left-hand side, is V. That's what I manipulate in my filter, in that matrix. Forget about this equation. We see filters are so simple. They are just figures. They're just 1, 2, 3 something, okay? But how are they calculated? That's it. Simple as that. General filter. There are some special ones. Now the question you may ask is that, what if I have red, blue, green? Okay, simple. You see here we have 2. You add another one here, and instead of MN, it now becomes MN something. 3 parameters. That's all. Nothing more than that. And if you can think of anything that is 4-dimensional, add another one, choose 4 parameters, and plug them into that equation. It works. It's simple. But you don't need to do that. I'm just, yes.
Well, it will affect V also, isn't it? It's going to be 3-dimensional also.
Yeah, it's going to be 3 too.
Okay.
And then if it is 4, it's going to be 4 too.
Right. Okay.
And so on and so forth. But I and K doesn't change.
Right.
I and K remain as they stay. Okay? So that's what we have. So let's move on now. Now, one other thing I want to show you quickly. You remember when we were talking about perceptron. You remember? Perceptron is simply this, and this. You remember? That's our perceptron. That's our neural network. Okay? So what have we done to our neural network now? To call it convolutional neural network, we've added filter. That's all. So your data, you know, all those pieces, they are coming in, they go into the filter first. The filter does its work, generates a result, and pass it into the intermediate computation. Now the intermediate computation does its work, pass the result into, remember, entropy function, so that the result that is going to be generated for you will be probability distribution, and so on and so forth. That's why that is called convolutional neural network. That's all, nothing more. It's because of the filter. So if you want to use what Professor Pius is using, MATLAB, you want to do classifier, and you want to do convolutional neural network, before you apply your classifier, whether it's neural network, whatever neural network, first of all, you apply filter to your inputs. So the result that the filter generates is the one that will pass into the classifier. Then you have your convolutional neural network. So you don't have to do it, you can do it on Waker, you can do it on MATLAB, you can do it with Python, you can do it with TensorFlow, doesn't matter. The only thing you need to remember is that the input comes into the filter, not into the neural network. It comes into the filter. The filter now work on the input, and whatever is generated by the filter goes into the neural network. That's convolutional neural network. Nothing more than that. Now, is it deep? No. Convolutional neural network is just like any other neural network, but specially designed for computer vision. Anything image, that's what it's specially designed for. Okay? It's a specialized one. Now, what makes it deep? Well, you have this slide. What makes it deep is this. If you read this, in a convolutional neural network, once an image has been filtered, now look at the next phrase, by several learnable filters. Now, it's no more question of single filter. It's now layers of filters. Okay? Several learnable filters. Each filter band's output is often aggregated across a small spatial region using average or maximum value. So that's what makes it deep. Because we are no more talking of one filter, we are talking of a lot of filters, each one generating and then passing on to different set of neural network. That's what we call deep CNN. Okay? That's what we call deep CNN. And that's all. It's an aggregation. That's what makes it deep. Okay? So if you now think back to feed-forward deep learning, it's several layers. Here now we are adding more to it in terms of the filter coming into it. And that's what makes it deep CNN. You can use convolutional neural network without deep. You can just use it with single filter and move on. Okay? So an example. I have this book at home. I wanted to bring it this morning, but it's big, so maybe I didn't carry it because it's big. So it's a data mining. By the way, the authors of Waker, the people who, they are the one that wrote that book. So if you are looking for a good book on machine learning, it's a good book to buy. I'll bring the complete reference later on. Okay? Now, another book on deep learning, a simple one that anybody can read. If you hate mathematics, is this one. You can read it. So it's Introduction to Deep Learning, but it uses TensorFlow. So you need to know something about Python to enjoy it. Okay, let's come back to the slide quickly, because I have 15 minutes left. If I photocopy the back cover of the book, that's what I have here. Unfortunately, this thing doesn't appear well. That should be in color. That first thing should be in color, but it's not showing. Okay? So now I apply convolution. That is, I filter it. It will generate something like this for me. Yes, please.
Can we use these filters to identify outliers?
Yeah, you can use it, but it's a different arithmetic altogether. What we are using filter for here is to identify the edges. That's number one. Number two, to identify the different feature in the image. And number three, to reduce the size of the data generated into the computation, because it can be big, really big, okay, to reduce it. So that's what, so you are going to see certain words that are used here. Something like pool. Pool here means that you apply filter, several filter, you pull the result together. That's what we call pooling. In image processing, they use it, pooling together. Then you see the word decimate. You reduce the quality of the image in order to be able to process it. It's called decimation. Decimate, okay? Decimation. Now, you can argue with yourself and say, why will I reduce the quality in order to understand it better? Just wait a minute, you will see why you need to do that. So, you apply a convolution, that is filter, you pull together, you decimate to get something like this, okay? And then you can do that successfully. Iterate that over a number of different filtering something. That's what we call D. And eventually, the result you get is what you pass on to your multi-perceptron. Okay, that's the result you pass on to that. Concretely now, how does that work? Let's go and look at something. I'll come back to that later on. Let me skip all the mathematics. The same image as before. Okay? Assuming the piece generated, okay, is that. It's X. It's a matrix. It's a vector. That's our X. Okay? Remember, it's a colored image, which means it's three-dimensional. I can only use three-dimensional filter. Okay? Now, I can choose any filter. The good thing about filter is that you can even devise your own if you know the arithmetic, but I'm not going there. I'm not going to explain the mathematics. It takes a lot of time. But there's this filter that are called Sobel filter. It's a group of filter developed by that the research group of that person. Okay? And you can use them for different things. They are two-dimensional, you have three-dimensional, you have different type of filter. They are used a lot in research. So we pick two filters from Sobel library. The first one is WX, the second one is WY. We apply WX, okay, to that filter. Remember, that filter too is a three-dimensional. So that's our, what is it called? WX. We apply it to that. Remember the dot product? It's a field, a matrices, sorry. So it changed this image into this. Are you with me? We apply the second, no, it produced the image. No, it changed this image to this. Sorry, I'm jumping. It changed this one to this. We pick the second one. We apply it to this. It changed this image to this. As you can see, the two images are still not really good enough. How do you know this when you are doing machine processing? Because generally you don't output all these things. You can output them, okay, but it takes a lot of time because it has to go into another filtering and then so on. But the way you see is that you look at the accuracy, the entropy, and so on and so forth. It tells you the quality. Now, instead of doing that, we now decide, okay, we are going to apply both filter at the same time to the same image. But we are going to even do better than that. We are going to take the notion of Euclidean distance. Can you see all this arithmetic now? You see, if you know the arithmetic, you can do a lot of fanciful things. Okay? We are going to now plug those distances into a Euclidean norm. Remember last week I talked about Euclidean norm. Hello? You still remember that? Okay. So you apply that idea of Euclidean norm, and then you now apply it on this image, and then you produce that. You can see that this is better than the previous two. Okay? So the amount of time you spend in image processing is actually dealing with filtering. Two things here. This image is decimated, but the important things that we need from the image, for example, data mining, practical something, those are the things we want to read. We can read them better compared to this, compared to that. Number two, the size in terms of volume of this may be probably 5 to 10% of that. So it's reduced. It's reduced completely. And then you can process this. Actually, you can see the different points which you can actually compare compared to the original of this one that is produced. So that's what we call filtering. Now, the mathematics is there, but I won't go through it. Convolution and correlation, they are just the same term used differently. So let's leave the mathematics alone. Now, the good thing is that the reason why at times we make use of deep learning in convolutional neural network is because you need a lot of layering, processing, in order to come up with an image that is actually interpretable. So if you pick up this image, that's the first layer. It's not good enough. The second layer of filtering makes it better. The third layer, you can now see some formation here. You can see the head of somebody, the hair, the mouth, something. But by the time you apply the fourth, the fifth, this will become clearer. And in biomedical system, this is what they do. They spend a lot of time filtering. Actually, more research is done in finding better filters. So it's no more just about machine learning, it's now about filter. That is what they do in biomedical system. Because if you want to predict cancer, you want to do this thing, you need to be able to train your machine with something that the machine can actually understand. And the better the filter, the better the result that is there in terms of trained model. Now, if we come back to mathematics, what are we saying? I have image, I pick up a 3x3 filter. That's my filter here. Okay? As I told you, filter is simply a matrix. There's no magic there. That's my filter. And then I apply that filter to the image. Remember, my filter is 3x3, but my image could be, for example, 28x28. But I have a 3x3 filter. Okay? Tolu, if you are listening. So I have a 3x3 filter. So I need, in TensorFlow, I need to be able to stride. That is to walk through my image. I take my 3x3, I apply it here. Okay? Then I define how many jump I need to do. That's what we call stride. If it is only one stride, then you make it 1 in your TensorFlow. If it is 2 stride, that is you want to jump 2, it's 2 stride. So assuming my stride is 1, I will move my filter 1 step. Okay? So, you know, it started by covering this, then I move it 1 step, I move it like that until I cover everything. Are you following? Yes. And once I get to the end here, it's possible that the last thing I need to do, this is the 27th, you know, this is 0 to 27. This is the 27th one. Then this side, there's nothing. Then I have to apply padding. Are you with me? So I pad this one with 0, 0, 0, 0. So that when I put my filter on top of it, it fits. That's what we call padding. That's what TensorFlow use, padding. So I do the horizontal, I do the vertical. Then, having done that, I now convolve the result, okay, by pulling them together. You see here, the result of one filter, which is 3 by 3, is pulled into one location. That's what we call pulling. Pull them together, pulling. And then I get this. And then I apply maximum pulling. What is maximum pulling? I'm choosing the maximum value in each pull zone. So if I look at this zone, it's 3. I put 3 here. That's my maximum value. I look at this zone, it's 0, I put 0. I look at this zone, it's 2, I put 2. Here is 4. At times, it may not be regular like this. It may be different number. So you just pick the maximum. That's what we call mass pulling. I put it here. So this is what I'm going to process. I'm going to send into my neural network process. So you can now see, starting with something like this, and then you can see, number one, you've made it better in terms of recognition. Number two, you've reduced the size. And number three, the computational time is also reduced. Now, you may want to argue with yourself that why do you need to decimate an image in order to make it better? Now, you need to go to those working in vision to ask them the question why. But I can tell you, it's working. It's working. The better this is, the better the prediction. Okay? So that's what you have there in terms of convolution. So I'm trying to get away from the arithmetic for some people, but these are just symbols. They don't mean much actually. Layers and gradient move. Yeah. So the question then is, what pulling and subsampling layer, they are necessary because when you want to do what we call back propagating gradient through the mass or average pulling layer, is a computationally expensive thing, and you want to make sure that whatever you are sending back is actually something that will give you a good prediction. That's all. Okay? That's what you are doing there. Implementation. Okay, this is the last slide. What this slide is telling you when you receive the slide is that convolutional neural deep network actually is better done on a GPU architecture. It takes a lot of time. A lot of time. Now, what is my suggestion here? You can use convolutional neural network to do anything, but it's specially designed for computer vision. And the reason why it's called convolutional is because of the filter. That's all. If you are dealing with a problem that doesn't need filtering or high-level filtering, then don't waste your time using convolutional. Okay? Number two, you can program convolutional on anything. You can use your MATLAB. I've explained before. Make sure that the data goes into the filters before it goes into your neural network. You can use TensorFlow. Okay? You can also use Python by using the library function if you know how to manipulate it. Okay? And so on and so forth. There are so many things you can use. Okay? So, August 3, I'll be around again. All of you doing work on language, natural language processing. If you can show up, you will gain 1 or 2 things on August 3. I'm going to talk about recurrent neural network, and that is specifically designed for natural language processing. And we're going to talk about LST2, long shots, something which is a typical, and then we're going to talk about word embedding, which is language processing, sentence embedding. We're going to talk about that, which is also language processing. Okay? So that's what we're going to do August 3. So I'm done for today. Over to Professor Pius.
Yeah. Do you have a copy of, I think I've calculated it wrong. You see it is called student lecture note. I've upgraded it. You can copy it. Have you gotten it? If you have not gotten it, raise up your
Flash
hand.
now.
Let's see a book.
You're still alright.
I just got it now.
Yeah, I think we can do it row by row. Since you can copy it, I think you can copy from this row so that those people on that side can start.
By the block. Anyway, let me just.
The one
Sorry, can you check? No, that's the previous one. I've updated it. Yeah, you will see the student lecture notes. The last week one is also there. I think they give it to you.
fantastic one I have.
That's perfect.
Thank you. Sorry, I'm not be able to.
No, it's fine. I think we're gonna speed up to this. You'll be fine.
I think I'm
You have completed.
No, actually, I need to see her and Professor. Can we go now and talk?
okay.
Or you still want to do something here? Maybe you can come back later. Can we go now? Or she want to?
Yes. I'm using them, so I.
Oh, okay.
Next week is fine.
Okay. So which one are you starting first?
Naive base.
Naive. Oh, okay. Okay, that's it. So he's starting that one first. So it's your lucky day.
We all have the lecture note now.
See, I don't know.
Okay.
Are you not connected?
This week apa maknanya lah?
Oh,
It's very missing.
just copy it.
Are we okay now? Are you ready? Are you all ready? Yes. Okay. Okay. last week we started with data processing, as I've told you. Remember I said that when we talk about machine learning, we're talking about supervised, unsupervised, semi-supervised, and reinforcement learning. Okay. Now, when we talk about supervised one, there are two things it does. Basically, it does the prediction, then it does the classification. Then more on supervised, you're talking about your clustering, basically, which does that for you. Now, last week I made you to understand the classification that when you look at this, I just narrow it down in the sense that we have supervised learning and we have unsupervised learning. Under supervised learning, we have two aspects, which is basically your classifications and your regressions. Okay? Where under unsupervised, you have your clustering sitting down in that place. Now, when you talk about classification, we're talking about where you use your support vector machine. I think next Saturday, I'm going to cover this. Today, we have what we call a discriminant analysis, which we will do today as well, if you don't get hungry and hungry. Now, then we look at the naive base today. We've talked about the nearest neighbor last KNN last time. Then the linear regression, we're not going to talk about that. On Saturday, we will look at, under the regression, we look at a sample method, which is very, very interesting type of a regression that we look at. Then we look at the decision tree today as well. We've done neural network already. Then we will look at clustering, which is we will look at the K-mean. I'm sure Prof. I'll show you how to use Waker to do K-mean, and you will see how MATLAB can make it very flexible and you can play around it. Then we look at Arachika method, where we basically look at your PCA, principal component analysis. You know, that's what we're going to do. But everything next Saturday, we kickstart 9 o'clock and we go up to 5. Hopefully, we'll be able to cover everything you're supposed to cover with me, basically. Just make sure you come with a bottle of water, and I don't think Prof is not paying for that food.
No, there is no food next Saturday.
Just come with your abani bread and mass. But I'm not sure if we get salary by then I can buy a bucket of KFC for people who doesn't want to lose weight. Okay, now, what exactly do we mean when we talk about a naive base? What do we mean? Now, a simple naive base expression normally have this simple expression there. Okay, that's a simple expression that we have. Now, we simply say the probability of A given, this slope is given B. Are you following? Prof said it last time, that you have the probability of A given B, okay? That's the simple meaning of that. Now, where this one is a probability of B given A that is true, and where this is the probability of A being true, and here is the probability of B being true. And that's a simple expression we have for naive base. In your lecture note, I put this index there. You just click it, you have a comprehensive example and simple way to attend to naive base. Another way people normally talk about it is that everything you see here is basically your posterior kind of probability that you have there. Then the other part is basically your likelihood and multiplied by your posterior parallel. Then you have your evidence, which is this. Now, since you understand the simple expression for naive base, what did they do as a whole? We have different classes or different categories of parameters, and we have intention to be able to classify them. The naive base will be able to classify them using the probabilistic approach that you have there into different classifiers. And you can see here we have about 3 different categories or different three different classifiers. And that is why you see this division simply break them down into that category. Let's make it very simple. I will make it very simple for you. Let's have this particular case study. Let us consider a class of a certain subject. In that class of certain subject, we have this amount of female, which is about 300, since they are more than us in population. Then we have male, which is about 200. That is the number of female in that class, in the general class. Now the question is this, is that 1% of the entire student in the class, they fail the course. Okay, 1% of them. Now, we now observe that among those students who failed, 50% of that are male, 50% are female. Thank God, equal. That's okay. Now, the question is this, what is the probability that a student will fail, given he is what? Not female, male. Now, that is where naive base become very interesting. Now, the question we are going to ask ourselves is now, how do we deal with this particular problem? If you remember earlier on, we have the probability of A given B equal to the probability of B given A multiplied by probability of what? A. Good. Divided by probability of what? B. Good. Now, how do we express this? In other words, we are looking at that the first thing we ask ourselves is that what is the probability of that particular female? Remember, when you understand probability very well, is your given number divided by the total. Where we have for female, which is 300, divided by the sum of the people in the class. Then we have that probability. Now, the probability of male now is what? Is 200 divided by that. Now we have our probability of that particular kind of state. Now, what is it presenting? Now the question is, the probability of people who fail is 1%, which is given by 0.01. Are you okay with that? Now, what is the probability of A giving B, which means the probability of male giving fail? Do you get it now? Which is this? Probability of male giving fail. Do you get it? Now, how do you determine that? Is now, we now say that 50% is given already. And you remember 50% of them fail, 50% of male fail, 50% of female fail. Now, that is the 50% you see, which is equal to 0.5. Okay. Now, what about the probability of female giving fail? Are you following? Now, in other words, what is that? We have 0.5. Now, our simple general expression, the question now is, what is the probability of failed giving what? Excellent. Now, can you now express that giving expression, this expression in this form? Now, we express that expression to use that expression to solve this problem. Now, if we express it this way, where this is A and where that is B, what are we saying in essence is that, what is that going to be? That means your B is what?
It's male.
Are you following? Then your fail will be good. Multiplied by, what is that? Your A. What is your A now?
It's fail.
Your A is what? Fail. Divided by?
Male.
You see how to apply naive Bayes to solve a simple problem. Is that simple enough? Do you get that? Okay, good. I just want to whet your appetite to see how easy it is. Now, we apply it now. By the time we do that, remember we've gotten the probability for this, for male giving fail, which is 0.5 multiplied by fail, for probability of what? Of fail, which is 0.1, divided by what? 0.4. And that is how we got 0.0125. And that is a simple application of naive Bayes. Yeah.
Probability of fail is 0.01.
Is what?
0.01.
Is 0.0 here.
No, I
Up
mean
there.
the probability on fail.
Okay.
Yes, on the last formula now.
Which one is that?
The last one is
You said 0.
Yes. Oh, okay. 0.01. Okay, you can put your calculator there
And
and
just move the result one place, one decimal place
Yeah, and
to
do
the
it.
right.
and do it yourself. Okay, now you get the application of it. The aim is to show you the application of it. Do you get it now? Now, let us look at a little bit in a factorial form. Let us look at it in a factorial form. Now, when we look at it from a factorial form, let's say for a feature of vector of x. Now, the naive Bayesian classifier will predict a class of probability as follows. Now, remember that we have A given B earlier on. Then we have what? Probability of x. And where this means that x here will be a change of numbers. You can have x1, 2, 3, where all these will be numbers. And you have been given this particular variable where these remain constant. Are you following me? But you have a change of items, of classes, or simple, what do you call it? Prof, where you have, you call them, there's a name that, not attribute?
Features.
Features, yeah, okay. We have them like that, okay. Now, when we have it in this way, how do we now represent it? You remember Prof was talking about the product, the summation, all this earlier on. That's what those sound. Now, let's see how we will simply, I'll make it simple for you. Prof is too advanced, but I will make this to make it simple. Now, when you have this, now let's see the probability of x given c. It's simply, we can reproduce it in this way because this is xr. And these are 1, 2, 3. Then we have these. Giving c.
The probability of x giving c. I need more explanation on giving c. What does this stand for?
For example, you see, when you have a probability of x, you have a probability that you have some items which are like classes of numbers. X, let's say we have x, we have item here 2.5, 3.7, 9.2. These are your x. But given x is a constant variable. You have a constant variable. You have a given constant variable. But you have a change of all these variable x. But this is fixed. Then how do you treat them? Remember, we don't use a product value in the earlier case. And that is why you always see when Prof was talking about n equal to 1 up to maybe 7. That means you have item from 1, 2 up to item 7. Now, how do you deal with that kind of case? Are you following? Then we regenerate that formula, which was static formula before, into a series formula. Are you following me now? Now, that's what we want to achieve here. Now, when we do this, what we end...
Can I say the value of x depends on c?
Given c.
Yeah.
Yeah.
Because guys talk about the conditional probability.
That's correct. As Prof.
Yeah, is okay. In the case of the example Professor Pius gave before, probability of male giving failure. So that means when you pick up a particular male, you look at the result. If it is F, if it is fail, that is within the set. You pick up the next one. If it is F, it's within the set. You pick up the next one. If it is P, it's not. You throw it out. So all those that fail. So your x1, x2, x3, x4 will be each x satisfy C.
So I can easily use this set theory, where you use linear and intersection.
No, I know where you are going to. No, no, it doesn't work that way. Probability doesn't work that way. It will work for some. Equality probability, yes, it will work. Inequality probability, it will not work. Just take it that the set x1, x2 up to xn, each one of them satisfy the condition, the constraint C. That's all.
Okay, I will also make it simple for you. There are girls, there are boys in a class. Yeah. But we don't know which one of them, there is a dependable condition they fail. which one of this one, X1, X2, which one of them fails? This fail is consistent. It's about failure. Okay, but we don't know which of these actually failed. Are you following me? We want to predict who among these actually failed. Therefore, you can't do further. Okay, now we have that now. Now, to make the equation a little bit friendly, this is equivalent to this now, so that we'll be able to say I equal to 1 into that xi, where your xi are x1, x2, up to the value of n. Therefore, remember Prof explained all this when he was starting with us, summation, he was telling us how those, each of them would be. Now, we've summarized them. Now let's see application in a simple way. This might be very useful for people who are doing language. I'm not a very good expert there. And people who are working on spam, virus, and all those stuff. Now, let's now get this, let's play with this expression. There is a email classification that I have. And I think I've seen this example also with Prof. Email 1, email 2, email 3, email 4, email 5. I have that emails. And in that email, we are able to say, hello Bob, laptop win, science, university, student that. For me to say that particular email is legitimate. Like it doesn't have a virus, it's free, it's not a spam. Now, I must have this particular case. For example, the win, the science, the university that show that email is legitimate. This also shows that email is legitimate. And this also shows that that email is legitimate. The other two shows that the email is not legitimate. Now, there is another traffic of email that comes in. And in that traffic of emails, the new emails, I need to classify if I need to discard that email as a spam or I need to accept that email as a legitimate. Now, how do I deal with that? The naive bias becomes something I want to use to solve this problem. How do I solve it? Now, if you look at this, you can look at it where you have 1, it's crucial. This is where you have 1. The 3 point is where you have 1. That means you have hello, you have laptop, you have win. Now, if I have that, what does that speak to me? And let's quickly go into this particular expression. Remember, our equation is still, you remember your A giving B, that, you still remember. Now, let's interpret that in this format. If I use this as a complement, C as a complement, that is my spam. Are you with me? Without complement, that is my legitimate. Are you okay? Now, I'm expressing the two expressions, the legitimate and the spam. Are you with me? Now, if you are clear with that, then what am I going to have? I'm going to have this probability of this, which is C, which is the legitimate, into that product of that and giving that multiplied by this. The same way is this. Are you with me? And the interest is to find the classification, which one is going to happen with that email. Is it going to fall here or is it going to fall here? Now, by default of the ratio, you know this value will go, isn't it? If you have x over 2 ratio x1 over what? Over 2. This goes, you have x dot x1. Is that correct? Now, I want to find the relationship. Obviously, this go, that go. Then I'm left with that, and I'm left with that. Are you with me? Okay, good. Now, since we have that, the condition is that, I'm setting the two conditions. The two ways to classification decision will occur when it is legitimate. It will be if this P giving this is greater than this. Otherwise, it's what? Spam. Now, we said that it's clear. Now, let's go and play with the figure. Now, for us to have this, remember, for us to have the probability of what? Of legitimate. It would be the number of legitimate mail divided by the total what? Emails. Total emails. What is the number of legitimate mail? 3. What is the number of spam? 2. What is the total number?
7.
Is what? 5. That means you have 3 over 5, 2 over what? Over 5. For PC, you have 3 over 5, that is that. For the sperm, which is what?
0.5.
Good, you got that already. That means you've dealt with the what? You've dealt with this, you've dealt with that. Are you with me? Good. Now let's move on to deal with the other side. Okay? Now, how do we deal with the other side? If you look at this is given in this product form, that means we have 3 states that shows from the given expression, which is hello, laptop, and win. Let's go back and see that table. If you come here, hello, laptop, and win. All other one, because the probability of 0 over what is just 0. We get that out. Now, let's go now and use that probability. Remember, it is x. We have hello into whatever, into C, laptop, into that, and we have that. Now, the question is this: what is the probability of hello that in this case? Remember, if you go back into this, if you go back to this this table, remember your hello in this table is, if you look at it, how many of them? How many of them? Look at it. How many of them is on the legitimate? Remember, it's legitimate. Your legitimate stop here. How many of them is 1? How many of them is 1? It will be 1 over what? 1, 2, 3. Are you with me? If you come to the laptop, how many of them is also 1? Am I right? 1 over 3. If you come to which other one? Win. How many of them? Good. That is how we resort to get this out. Are you with me now? Now let's go to the sperm now. How many of them, if you come to sperm? If you come to sperm side, we're looking at anything between here. Now, if you look at this, how many of them are 1? Then you will have what? 2. 2 over what? 2. And how many here do you have?
2 over 2.
It will be 2 over 2. Now, how many of them are here? 1 over what?
2.
Therefore, 1 times what? Half. Okay, that's how we resorted to that. That's how we got that. Then you have them together. Are you okay? Now, since we've gotten mostly all the parameters that we need here, let's see the way we combine them together now. Remember that we're able to get 0.6 multiplied by 0.037. Then for the sperm, we have 0.5 multiplied by that. If you look at this and look at this, the question is this: under our set condition, if you go back, our set condition was that it would be legitimate if the what? For the legitimate is greater than sperm. Now the question is, if you look at it, which one is greater? Is the legitimate greater or sperm greater? We show that 0.2 is greater than 0.0022. Now the question is this: is this item here, this item is sperm or illegitimate? Is what?
Sperm.
That's how it does the classification. That's how naive bias does the classification. Do you see how simple it is? And how do you use it as a classifier?
Let me quickly say this.
Okay.
For those of you working on languages, if your language, if you are translating from one language to the other, and the positioning is not maintained, your bias, something will not work well. Because bias work with positioning. Look at hello, Bob, and all that. When we got another email, we plug it into the same pattern. So if you can do that, it will work fine. If you cannot, it will not work well. It will work, but it won't give you a good result.
Okay, is that clear now? Yeah, you have to brush up a little bit, but it's okay. But now let's make it a little bit, let me give you one simple another example. Let us say we have a case study of this. I have a star, let's say a star, a cluster star of this, and I have this, I have this, I have this. Now, if I make X, for example, not cheat, and I make 0 cheat, like you cheat in class or cheat in the transition. Let's make it this way. I call it, I will use the estimated salary, because we have been using that, estimated salary. And I have this as a number of transactions. Okay, I have that as a number of transactions. Okay, if I have, for example, under the not cheated, to be, let's say we have a cluster of almost something up to 20, and where we have number, like this point, there are 10 in numbers. Okay, I have that as 10 in numbers, for example. Now, I want to apply a numbers that is a item that suddenly fall in this item. It just drop around. I cannot classify this. The question I don't know. Should I group it under not cheated or under cheated? Are you with me? Okay. Now, that is the question that I have. Our simple expression we know is what? P into A, given that B equal to what? Probability of what? B given by A, multiplied by what? Probability of what? A. Over what? Probability of B. Now, that's good. Now, we have that now, and I wanted to translate it. Let's translate it into cheated and not cheated. Are you with me? That's what I want to translate it to. Can you just tell me, I want you to give me the expression for that. Cheated and not cheated. I want you to write it down by yourself and let me know what do you feel about it. Remember, this is my new letter. I'm going to represent it with X, okay? It will be probability of the first one, let's say not cheated, okay? Giving what? X. Are you with me? Equal to the probability of what? Of what? Of S giving not cheated. Good. Multiplied by what? Probability of? Good. Probability of not cheated. Okay, good. Over probability of X. Good. That's what we for have. Now, what about the next one? What are you going to have? It will be probability of cheated into giving X equal to probability of X what? Cheat. Multiplied by probability of cheat. Remember, we've done the cheated, now cheat. Okay. Over probability of what? X. Good. That's what we have. Now, since we have that now, the question now we are going to now outline is, what is, let's start with probability of cheat, probability of not cheated. Okay, let's just start with that. And the other point that I think we can look into is that, now, for the first one, not cheat, what do you think it will be the answer? Remember, the total number that I have for cheat is what? 10. Okay, that's 10. Now, I have 20 here. The question is, remember the probability is the number of this divided by the summation, the totals. That means I will have, for this, I will have what? 10 divided by what? 30. Good. Then I have what? 1/3. Is that okay by you? Okay. Now, the next things that we need to look into is to find, I think, let me just do it one by one so that I don't mix it up. Okay, let's do it this way. The next thing that we are going to look into, we're here, is what is the value, the probability for X. We don't know. Then what is the probability for X and this cheat? We don't know that. What do we do? Now, if you look at this, because we have not classified this, we don't know it's either not cheated or cheat. We don't know. But we want to find a probability for it. How do we do it? Now, we use, you remember Prof was talking about we talk about the KNN earlier on. What we do is that we will try to look at what items are very close in that particular region. Are you with me? Now, for example, if I have item here and I have one item, let's say I have another item here. I will draw a circle around that item. What I will study is not this item because I don't know what classes it is. I need to find the class in which it will fall. But I know the classes in which all these three are. Are you with me? Are you with me now? You see, I don't know. I cannot do this by saying that, oh, this belongs to not cheated, this belongs to cheated. I can't do that because I've not assigned anything to this. What I will do, I will take the neighborhood. I will take the classes in the neighborhood. I will find the probability of proximity to this probability. And that is exactly what I intend to do now. Now, if you look at this, if I want to find the probability for this, what do you think will be the probability here? It will be what? What do you just guess by yourself? What will be the probability that we expect to have there? It will be what? No, it will be 1, 2, 3, 4. It will be what? 4 over what? 30. Because I cannot do, it cannot be 1 over whatever because I don't know. Then I use the neighborhood to find the probability of the neighborhood. Are you okay now? Okay. Okay. Now, the next thing is that we want to find what would be the probability of this, of X, given cheated. Are you with me? Now, if you look at it very well, we say the number who have cheated, it will be the number that have cheated, okay, have cheated over what will be the total number of who? User who have cheated, isn't it? Am I right? Over the total number who have cheated. Okay. What do we call our cheated? It will be what? What will be our cheated? It will be what? It will be 10. That's correct. Now, but one thing I want you to look in here is that how many of that cheated is close to this? Is what? Good. You are a brilliant one. 1 over what? 10. Thank you. You've solved the problem. Do you get it now? 1 over 10. Now, I want you to now do for cheated for me. Let's do for, we've gotten the parameter because we can slot them in. Because now we have the cheated, which is that. We have the probability of X, which is that. And we have for this, which is that. We have that already.
Let me confirm, Prof.
Yeah.
When you were counting the probability of the number of not cheated, you counted those X like 1, 2, 3, 4, there are 4. You included even the one without.
Sorry?
When you, okay, let's start with the first one. The one.
This one?
Yes.
Yes.
When you say it's 4, you counted like 1, 2, 3. Those 3 X including the one without.
Yes, including this inside, because we don't know if it is here or there. We don't know. We take the neighborhood to find out probability for the neighborhood.
Okay.
That's what we do.
Okay.
It's at the end that we'll be able to justify that this particular item is here or is there. We use the neighborhood. Now, let's play. I want you to now play with not cheated. Let's do the not cheated. It will be probability of not cheated. I will use the word n cheat on it, okay? Into X equal to probability of what? Probability of what? X, giving that not cheat, multiplied by probability of what? N cheat. Okay, divided by P of X. Good. Then we carry on with the same thing by doing that. Now, if you look at what would be the probability of not cheat, probability of not cheat. We have already gotten that. Where is that? Not cheat. What will be the probability of not cheat? It will be what? 20 over what? Over 30. That will be what? 2 over 3. Are you with me? Now, the next question is that what will be the probability of x now? What is it? It's going to be the same. Thank you. It will be 4 over 30. Okay. Now, what will be the probability of x giving no cheat? What is it? It's the number of what? Of not that have not cheated over total number of the cheat. Now, what will be that? Can you tell me? What is it there? Everybody tell me, what is it? 1, 2, 3. It will be 3 over what? 20. Good. Are you following? Now, let's do this. This is probability of not cheat. Come here. Here is x. Probability of this is there. And this is here. Take your calculator, work it out for me, and let us know which one is greater than the other. Then we'll be able to do the classification for this item. Do that quickly. Play with it. Cheat should be giving you what?